in this problem, we're given a family of 2 children, and we're also told that we have this characteristic C. So this characteristic, for example, could be born in winter. And we are told that the probability of a child having this characteristic is P. So let's let Ci be the event that the ith child has the characteristic C. And so we're told that probability that the ith child has this characteristic is little p, and this is independent of the gender of the children and independent of each other. So given that one of the children has this characteristic, tells us nothing about whether the other child has this characteristic, and also knowing the gender of a child tells us nothing about whether that child has this characteristic or not. We're also going to let Gi be the event that the ith child is a girl. And we're interested in finding the probability that both kids are girls, given that at least one of them is a girl with characteristic C. So to solve this, we're going to use the definition of conditional probability. So we're going to look at the probability of the intersection of G1 intersect G2 and this union of these two sets. So G1 intersect C1, union G2 intersect C2. And we're going to divide that by the probability of G1 intersect C1, union G2 intersect C2. So can we somehow simplify the expression in the numerator here? Well, notice that G1 intersect G2 tells us that both children are girls, and we're intersecting that with the set that tells us that at least one, so at least one is a girl with the characteristic C. So we already know that both are girls. So we can rephrase this by saying both are girls and at least one has characteristic C. So we could rewrite this as the probability that both kids are girls and at least one has characteristic C. And we can rewrite the denominator. G1 intersects C1, union G2 intersects C2. Now, we're operating under the assumption that the gender of the kids is independent of whether they have the characteristic, and also having the characteristic C is independent amongst the kids. So knowing that one kid has the characteristic C tells us nothing about whether they have the other child has characteristic C. So this probability of these intersections can be written as the product of individual probabilities. So this is the probability that the first child is a girl times the probability that the second child is a girl. We get 1/4 there, times the probability that times the probability of this union of these two sets. And we can write that as the probability of the first set C1 plus the probability of the second set C2 minus the probability of their intersection. And the probability of their intersection C1, C2 is p squared, again, because having the characteristic C is independent between the children. So knowing that the first child has characteristic C tells us nothing about whether the second child has characteristic C. So we can just multiply those two probabilities, p, to get this p squared. And now we divide this by, so again here we're gonna say we're gonna break this down. We're gonna say this is the probability of G1 intersect C1 plus the probability of G2 intersect C2 minus the probability of the intersection of those things. So G1 intersects C1 intersected with G2 intersect C2. So in the numerator, we have 1 over 4 times 2p minus p squared. Now in the denominator, the probability of G1 intersect C1, again, gender is independent of having the characteristic. So this is 1/2 p plus, by symmetry, same goes for the second child, 1/2 p minus the probability of the intersection here. So this says both are girls with characteristic C. And again, gender between kids are independent, and having the characteristic between kids is independent and is independent of their gender. So we can just write this as a product of individual probabilities. So both are girls, that's 1/4, and both have the characteristic C, that's p squared. Now, simplifying this expression here, we get 2 minus p over 4 minus p. And now we can see that if p equals 1, in other words, if our characteristic C is extremely common, everyone has it, then having the characteristic C tells us nothing extra about whether the children are girls or not, and whether both of the kids are girls or not, and the answer reduces to 1 over 3. The probability that both children are girls, given that at least one of them is a girl with characteristic C, reduces to 1 over 3, which is the same as the probability that both are girls. Both are girls, given that at least one of them is a girl. So having the characteristic C tells us nothing here, because everyone has that characteristic. On the other hand, if the probability of having that characteristic approaches 0, then we can see that our result approaches 1 over 2. So the more rare the characteristic is, then saying that at least one of the children has that characteristic is more like specifying exactly which child has it, because it's an extremely rare characteristic. So if you tell me that one of the kids has it, it's almost like saying specifying which child has that characteristic. And so the probability then of both kids being girls is the probability of the other child being a girl. And the child is equally likely to be of either gender, and so the probability that they're a girl is 1 over 2.